Hello everyone, welcome to Analog Electronic Circuits, lecture number 19, part number 2, and in that part number B. So last time we have started with the discussion on Darlington pair, and we have seen that Darlington pair, why it is called as a super beta transistor, because it provides the voltage current gain as the product of the individual transistor current gains. That is, your current gain is beta 1 into beta 2, whereas a normal transistor can't provide such a high current gain. Next, we saw that the we will build an amplifier using Darlington pair. So next we used the emitter follower or common collector amplifier using Darlington pair, where over here, as we can see, the normal transistor BJT transistor is replaced by a Darlington pair. And we started with the DC analysis part. So in DC analysis, we have applied the Thevenin's equivalent at the base 1 terminal, and we found out the equations for RTH, VTH, and IB1, and similarly IC1. And then we applied the KVL at the output loop and found out the equations for VCE2 and subsequently the other currents also, IE1, IC2, and VE2. So we have completed with the DC analysis part for the emitter follower amplifier using Darlington pair. Today, our focus will be on the AC analysis. So let's begin with the AC analysis part for today's lecture. Okay. So for AC analysis, we will start with today's topic, that is emitter follower amplifier using Darlington pair. So in the AC analysis, we will be finding the input resistance Rin, the output resistance Rout, the current gain, overall current gain AI, we can call it overall current gain as AIS or AIT, and the voltage gain AV. So these quantities we will be finding out for emitter follower or a common collector amplifier using Darlington pair. So let's start with the analysis. So this is the circuit diagram of emitter follower amplifier using Darlington pair. Since the input is applied to the base and output is taken from the emitter terminal, that's why it's a emitter follower. Remember, emitter follower provides almost a unity current gain, unity voltage gain. Its current gain is high. So using a Darlington pair, the current gain can be increased up for the high value. And over here, we have small signal AC, and we have an internal resistance RSig. Then we have input coupling capacitor. And here at the output also, we have output coupling capacitor. So input is a small signal AC, that is Vs, and output Vout is the amplified form of the input AC. In this case, it's unity gain. And over here, we are using this composite transistor Q1 and Q2 will form the Darlington pair, right? And we applied the DC voltage so that the transistors are biased in the proper region of operation, that is forward active. Now, for the AC analysis, we do the following. So for the AC analysis, we will short circuit connected capacitors, will short circuit connected capacitors and DC sources. So over here, we have wherever you see a capacitor, replace that with a short. So I'll be soon doing that. Yeah, and here there is a DC source, so that also have to be replaced by a short circuit, that is ground. Okay, so I'm marking that with a red color. So here it is a capacitor replaced by a short, and over here another capacitor replaced by a short. Then this DC source is also sorted. Yeah, so this is my AC analysis part, and it will be very helpful if we write the terminal names for both the transistors Q1 and Q2. So here it is base 1, collector 1, and collector 2 are connected together, and that is connected to the ground. Then emitter 1 and base 2 are at the same point. Then that is, yeah, emitter 1 and base 2, and emitter 2 we have connected RE, and that is also going to the output Vout. Now next what we do is we will be replacing M1 and M2 with its hybrid pi model. So your next step is replace Q1 and Q2 transistor with its hybrid pi model. So let's do that now. So we will be drawing basically mid-frequency small signal equivalent circuit. So let's write it down. What are we targeting? We will be drawing mid-frequency small signal equivalent circuit. So here we replaced BJT with its small signal hybrid pi model, and also short circuit the connected capacitors and the DC sources. So this is how your circuit will look like. Let me take some space over here so that everything is fitted together. So first of all, we'll draw the small signal model for Q1 transistor. That is base 1, collector 1, and emitter 1. So we start over here. Let me change the color to black. So from here we'll start, and let's draw. First of all, let me draw the base. This is the base, collector, and that's the emitter. Let me mark it. This will be base 1, and here we will have emitter 1, and here we'll have collector 1. Now, in a small signal model for a BJT hybrid pi model, between base and emitter we have R pi. So we'll write over here R pi 1 because it's for Q1 transistor. Between collector and emitter we will have a current source, a voltage dependent current source. Here the voltage will be V pi 1. Okay, even if we don't write it, that's fine, but yeah, and this current source will be gm1 into r pi 1. All right, so this is my small signal model for q1 transistor. Now let's draw the small signal model for q2 transistor. Now if you see carefully, the small signal model for q2 transistor, the base terminal emitter terminal are tied together, right? And collector terminals are tied together, emitter terminal is separate. So let's start with this. So emitter terminal and the base terminal of the Q2 transistor are connected together. For previous Q1, E1 terminal and B2 terminal are connected together. So here, let's say that this is my base terminal, base 2 terminal, right? And here I will have a collector terminal, emitter terminal, sorry. And the collector terminals are tied together. So here I will have a collector terminal only. So this is my collector 2, and this will be my emitter 2 terminal. So between base and emitter, what do we have? We have R pi 2. All right. And in between that, the voltage will be V pi 2. And between collector and emitter, what do we have? So between collector and emitter, we will have a current source going from collector to emitter, and it's gm. Okay, here it should be gm1 into v pi 1, and here it will be gm2 into v pi 2. All right, so we have completed the models, the two models for the transistor, q1 and q2 transistor. Fine. Now we'll connect the remaining part of the circuit. So let's go back. So from the base 1 terminal, we will have two resistors R1 and R2 in parallel. And with them, we have Vs and Rsig in series. So let's draw that. So let me take some space over here and draw R1 parallel to R2. So here it is, R1 parallel to R2. Let me write it down, R1 parallel to R2. And then in series, we have Rsig. Here it is Rsig. And this is the voltage source, Vs. There's a reason why I'm drawing this long lines. You will understand once I complete it. So this is my source Vs. Okay, so base 1 side connection is over. Then we go to over here, emitter and base 2 are already connected. Collector 1 and collector 2 are already connected. We'll go to the emitter 2 connection. So emitter 2, we have a resistance going to the ground. And from there only we have the output V out. So over here, and collector 1 and collector 2 are connected to the ground. So let's connect them to the ground first. So I'll take a wire and do the connection to the ground. Now from the emitter 2, we have a resistor RE coming out. So here we'll have a resistor RE, and that resistor will be going to the ground. This is RE, and across this resistor RE, we will have V out. So this is plus minus V out. All right. So this becomes my mid-frequency small signal equivalent circuit for emitter follower amplifier using Darlington pair. All right. Now, let's say that we wish to first calculate the input resistance, right? So when we first calculate Rn, we want to calculate Rn of the circuit. So let me take another color. Let me orange. Let me use orange with a thicker this thing. Yeah. So I wish to calculate Rn from year to year. This is Rn. All right. Now, in order to calculate Rn, it will be easier if I divide it into some task, simple task, right? So first of all, here, if I calculate this Ri, let me call this as Ri, resistance looking into the base terminal, base 1 terminal of the transistor. What do you see? R1 parallel to R2, right? And we have some a lot more information over here because we have resistance also over here, but different current flowing through them. So Rn will be R sig plus Ri. That much is very, very clear. Rn will be R sig plus Ri. Now what is Ri? So in over here, we can also calculate the equivalent resistance seen by the R pi 1. And we call that resistance as Ri1. All right. And next we see the resistance from the base to terminal. This resistance we call it as Ri2. This is for the simplicity, or else it will become quite complex. Okay. So these things are clear up till here. Any doubt? So what will be Ri? Rn will be R6 plus Ri. Okay. And then we will also calculate Ri1 and Ri2, incorporating all the previous terms. Okay. So let me start with the analysis. So first of all, we'll calculate Ri2. Now, what do you think? What should be Ri2? What should be the value of Ri2? Yeah, think a bit. What should be Ri2? So in this case, your value of Ri2, let me see if I have used. Yeah, that's fine. So Ri2 will be R pi 2 plus Re, but it won't be Re because the current flowing over here, is what? Ib2. This current is Ib2. And what is this current? This is IE2. What is the relation between IE2 and Ib2? So IE2 is 1 plus beta 2 times Ib2. All right, because IE is IC plus IB and IC is beta times IB. So IE2 is 1 plus beta 2 times IB2. So whenever, we can consider two resistance in series when the current flowing through them is same, right? So I can write Ri2 will be equal to R pi 2 plus, I have to multiply this 1 plus beta times Re. Then these two resistances will be in parallel, in series, right? Because current will be same. This current also will be Ib2 and this current also will be Ib2. That is 1 plus beta 2 times Ib2. All right. So let me write that down first. So first we will calculate Ri2, and that is coming out to be R pi 2 plus 1 plus beta 2 times Re. Okay. So we have calculated the value of Ri2. Now similarly, what will be Ri1? So Ri1, the current flowing over here, is IB1. All right. And from year till year, we have RI2. Don't need to calculate this RPI2 and RE again. Here we have RI1. Current flowing through that will be base current IV1. And then we have a resistance RI2. Entire resistance looking into the base 2 terminal over here, right? So it will be similarly, we can write it as this is RPI1 plus RI2. Now it won't be RI2 because here the current flowing will be IE1. Here the current flowing will be IE1. So what's the relation between IE1 and IV1? IE1 is 1 plus beta 1 times IB1. So now that the current is same, I can write RI1 as RPI1 plus 1 plus beta times RI2. Is that clear? Because this is the equivalent resistance seen from the emitter 1 to the ground, right? So let me write it down over here with clarity. So now what did we get? RI1 will be equal to RPI1 plus 1 plus beta 1 times RI1, where RI1 we can substitute this value over there. So let me write it that. So we can write it as that is RI1 is RPI1 plus 1 plus beta 1 times what is RI1? RPI2 plus 1 plus beta 2 times RE. So such a huge expression we are getting for RI, RPI, RI1. Okay. Now this can be approximated further. 1 plus beta can be approximated as beta because beta value is greater than 1. And here both the transistors Q1 and Q2, let me show it to you. Here both the transistors Q1 and Q2 should be matched. What is the meaning of Q1 and Q2 being matched? They will have same parameters. So let me add over here. Assuming transistors Q1 and Q2 have same parameters. So what do you mean by having same parameters? That is beta 1 is equal to beta 2 is equal to beta. Okay. And wherever I have beta 1 into beta 2, that can be written as beta square. Now here I will approximate that. Okay. So I can write this, I simplify this further as RI1, which is equal to, this will be RPI1 plus beta 1 times RPI2 plus this should be RPI2 plus beta 2 times RE. Okay. Further, I know that your beta 2 into RE, which will be much greater than RPI2. Correct? So further we can write beta 2 RE is much greater than RPI2. So we can further approximate this as follows. That is RI1 will be approximately equal to beta 1. Here this term will be not there. So beta 1 then RE into beta, beta 2 RE into beta 1 plus R pi 1. And if both the transistor parameters are same, I can say beta 1 into beta 2 will be equal to beta square. Okay. So we can finally write the approximate expression. And also, also one more approximation we can make that over here. Now, this beta 1, beta 2 into RE is huge compared to R pi 1. So we can say that R pi 1 is very much smaller as compared to beta 1, beta 2 into RE. So we can further approximate this as follows. That is RI1 will be approximately equal to beta 1 into beta 2 into RE, which can be further approximated as That is Ri1 will be approximately equal to beta times Re. So as you can see, it's a huge value. Input resistance is very, very high. This is very, very high. And what is this Ri1 basically? So Ri1 is looking into the base of your Darlington pair. So basically it's the input resistance of the Darlington pair. So as you can see, the input resistance of in case of a Darlington pair also is very, very high. So let me add over here. This is the input, not of the amplifier, of the Darlington pair. Input resistance of Darlington pair employed in emitter follower amplifier. Input resistance of Darlington pair is also very, very high. Okay, that's an advantage for a Darlington pair amplifier. Now, looking at the circuit, can you all tell me, again, I'll come back over here. Looking over here, can you all tell me what will be Ri? What will be Ri? Ri will be R1 parallel to R2 parallel to Ri1, because Ri1 is a resistance looking from the base 1 terminal to the ground. So Ri will be R1 parallel to R2 parallel to Ri1. Is this clear? Right? And finally, Rn will be R6 plus Ri. So yeah, and Ri will be the input resistance of the amplifier, okay, of the emitter follower amplifier, right? And what will be Rn? Rn will be the overall resistance of the entire circuit. Okay, so let me add it Ri. So what was Ri from here? Ri was equal to basically R1 parallel to R2 parallel to Ri1. This is very, very high value, right? So let me mark it, put it inside the box. Again, this is called as, this is the input resistance of the amplifier. Input resistance of the amplifier. Which amplifier? Common collector or emitter follower amplifier. All right. Here you note one thing, that even if your Ri value, Ri1 value is very, very high, whenever it is in the parallel combination, the resultant will be the lowest among all, right? I mean, lower than the lowest among all. So basically we can note that over here, the biasing resistors R1 parallel to R2 reduces the input resistance of the amplifier, reduces Ri value in spite Ri1 being very high, in spite Ri1 being very high. That means whenever you, as soon as you connect R1 parallel to, I mean, R1 and R2 in the circuit, it will reduce the input resistance of the amplifier. Without R1 and R2, the input resistance of the Darlington pair is tremendously high. Okay. And what did we say about Rn? Can we go back to the mid frequency small signal equivalent circuit? So Rn will be R6 plus Ri. Okay. As simple as that. So let us write it down. What will be the value of Rn? That will be R sig plus Ri. Is that clear? Yeah. So this is the input resistance of the entire circuit. Okay, of the entire of the amplifier, including the source. Okay, so this is input resistance, of the circuit, including source resistance. That is R sig. If R sig is 0, then Rn and Ri are one and the same. So in this manner, we have completed our discussion on finding the value of Rn, then Ri, Ri1 and Ri2. So in calculation, if it comes in the paper, then please calculate Ri2 first, then Ri1, then Ri, and then Rin this sequence. Fine. Now, let us focus our attention towards finding the current gain. Okay. So let me write over here, second point. This was the first part actually. First part was finding out the value of Rn. Let me add it over here. Yeah. So this is first part was calculation of Rn. Then next will be the current gain. So let me add over here only. Second part will find the current gain of this emitter follower using Darlington pair. So current gain, overall current gain I want to find. So I'll write it as AIS, or we can also write it as AIT, but that's fine. So let's find the current gain of the emitter follower using Darlington pair. So we'll refer this circuit only. And over here, we will be marking some currents because current gain will be output current divided by the input current. All right. So let me start from here. So let me first delete some things which are not required. Okay. So right now we are finding the currents, right? So first of all, this output current is called as I out. Let me mark it as I out. Current flowing through the register RE, we can call it as I out. Then here, the current flowing into the emitter terminal here is called as IE2. This is IB2. This is IE1. That is fine. This is IB1. And here, this we call it as I in. And this current we call it as a source current IS. So we have IS, I in, then we have IB1. IE1 will be 1 plus beta 2 times IB2. Then we have IB2, IE2, right? And then finally I out. Let me add I out as IS small. Okay. So this is I out. Okay. So these are the currents in the circuit. All right. This current is I out. Fine. So now what will be the overall current gain formula? So let me write it out. So overall current gain will be the output current divided by the input current. So output current is I out and the input current is IS. Okay. So we will not directly find that directly relation between I out and IS will be difficult at stretch. So we'll divide it into smaller parts. So first we will calculate I out divided by IB2 because IE2 and I out are one and the same. All right, because I out and IE2 are one and the same. So I out divided by IB2, then IB2 divided by IE1, IE1 divided by IB1, IB1 divided by IN, then IN divided by IS. So that way we will be calculating the value of A, AIS. So let's start with the analysis. Okay, so let's continue with finding the current gain of the overall amplifier. So current gain of the overall amplifier will be output current divided by the input current, which will be in the stages. I out divided by IB2, IB2 divided by IE1, IE1 divided by IB1, IB1 divided by IN, and IN divided by IS. So this way, stage by stage, we'll go back. So let's start and find out the current gain. So let me add over here IS, but that current will be I out divided by IS, which can be written as I out divided by first current will be IE2. I out and IE2 are same, but let's do this. I out divided by IE2 and IE2 divided by IB2 and so on and so forth. So let's continue further. Okay, so let me get that back. Yeah. So it will be I out divided by IE2 into IE2 divided by IB2 into IB2 divided by IE Let me check it out. IB2 divided by IE1. All right. That can be written as IE1 can be written as IB1 also. So let me write that also into account. Let me take that also into account. So IB2 divided by IE1, that is will be same. So it will be IE1, then IE1 divided by IB1 into IB1 divided by I in, and finally I in, sorry, I in divided by IS. So if you see, it's I out equal to I out divided by IS only eventually, right? Now let us find out what all these quantities are in the circuit diagram. Okay, so what is the relation between I out and IE2? They are one and the same, right? So the ratio over here will be 1. I out divided by IE2 will be 1 because they are the same current. So let me write over here, this will be 1. Okay. Also, one more current is same. What is that current? IE1 and IB2 are same. IE1 and IB2 are same. So this also will be 1. Okay. Now, what's the relation between IE2 and IB2? So let us check it out. Let's calculate that. So IE2, here we have written IE2 is equal to 1 plus beta times IB2, right? So what will be IE2 upon IE2 divided by IB2? So here we can write okay, let me add a different color. So IE2 divided by IB2 will be equal to 1 plus beta 2. Okay. Similarly, IE1 divided by IB1, IE1 divided by IB1 will be 1 plus beta 1. So we'll write that down over here. So this will be, let me use blue color only. Okay, give it some time. So this will be 1 plus beta 1. And let me go over here. Yeah. So this will be 1 plus beta 2. This is 1, this is 1. And over here, this will be 1 plus beta 1. All right. Now we have to calculate IB1 divided by I in. Okay. And this eventually, this IE2 divided by IB2 is basically the gain of the, you know, AI2. We call this as AI2. AI2, second stage gain, current gain, and this is AI1. All right. We have found out this before, but yeah, we are writing it down again. So here we can say that I out is approximately equal to IE2, and here we can give justification that IE2 and IB2 and IE1 are one and the same currents. Now we have to find IB1 divided by I in. So let's do that. IB1 divided by I in. Let's find out that. So let's go to the circuit. What's the relation between IB1 and I in? Okay, we can use a simple, current division rule, right? So let us find that first. Okay, so IB1 divided by I in. Here we have a resistance RI1, and here we have a resistance R1 parallel to R2. So let me redraw the circuit, and here we have the current I in, which is flowing. Let me redraw the circuit over here and show it to you all how it will look like. Okay, so the circuit looks something like this. So here we have R1 parallel to R2, and here we have the current RI. I mean, here we have the resistance RI1 going to the ground. Here we have the current IB1, and here this is grounded, and here the current flowing, which is I in. Now by a simple CDR, that is current division rule, we can find out the value of IB1 divided by IN. So what will be the value of IB1? IB1 will be R1 parallel to R2, the other resistance, divided by the total resistance into IN, right? So into IN, I can take it over here. So here it will be IB1 divided by IN will be equal to R1 parallel to R2 divided by R1 parallel to R2 plus RI1. All right. So that's the value of IB1 divided by IN. So let me add over here. This is the value which we are looking for. Here it is. Okay. Now last we have to find out IN upon IS. So let's go back to the mid-frequency equivalent circuit. Yeah. So here we have IS and here we have IN. So we can apply a current division rule and find out this. So here we have current flowing IS and here we have IN. So let me see if I can draw that circuit over here. Okay. So I'm redrawing the input circuit. So here we have a voltage source Vs. Then we have a R sig resistance. Then we have a resistance Ri. All right. So from here you will say that this current is IN and this current is IS. They are one and the same. No, they are not one and the same. What we can do is we can apply a source transformation over here. Okay, this point is we can apply the source transformation. So what will be happening? A voltage source will be becoming a current source. Voltage source will be becoming a current source. And we have in series a resistance, which is R sig. And then we have a resistance Ri. And this current is called as IS, and current over here flowing over here is IN, and this resistance is Ri. All right. So this resistance from here to here, let me show it to you in the circuit. So from this point to this point, we have resistance Ri. Okay. So that is what we have drawn, which is going to the ground. So now can we apply a current division rule over here and find out the value of IN upon IS? Yeah. So let's do that. So we'll find out the value of by CDR. We can write by current division rule. We can write IN, right? We can write IN is equal to other resistance, that is R sig, divided by R sig plus Ri, and that is into IS. So this IS, I'll take it down. I can call it IS divided by IN. So here it is. I got the expression for IN divided by, IN divided by IS. And here we got the expression for IB1 divided by IN. So the last term in the equation over here, we can calculate it like this. This is the expression. So this can be evaluated using this formula. All right. So when we multiply all those terms together, we'll get the value of AIS. So again, I'll write it down over here. The value AI. Okay, let me use a black color only for this. All right. So we can write over here AI1. Okay, AI1 will be equal to 1 plus beta 1. Then we have AI2, which is equal to 1 plus beta 2. Here it is. You can have a look at it. It's given over here. Right? AI2, we call it as current gain of the second stage. And this is the current gain of the first stage. This is 1 and this is 1. So finally, we write the expression for AIS now. So let us write it down. That is AIS will be equal to AI1 into AI2 into IB1 upon IN, which will be R1 parallel to R2 divided by R1 parallel to R2 plus Ri1. All right, and this multiplied by, we have In divided by Is. So let us check it out. We have calculated In divided by Is. Here it is. So this product will be multiplied by R sig divided by R sig plus Ri. So finally, we get the expression for the overall current gain, right? Now, current gain is normally a very high value. Now, if we have R1 and R2 present, then it will reduce the current gain, as you can clearly see from here, because this value of Ri is very, very high. Ri1 is very, very high, right? So that's why this presence of R1 and R2 and RSig also will reduce AI in spite of AI1 and AI2 being very, very high. Okay, so we can write it over here that note, let me use a smaller font. Okay, okay, note, presence of R1 parallel to R2 and the signal resistance RSig reduces current gain of the entire amplifier. Okay, in spite, let me slightly move up, in spite AI1 and AI2 being high. All right, so this is the value of the current gain, overall current gain, AIS. So next we move on our discussion and find out the value of the voltage gain, the overall voltage gain. We'll find out the value now. Okay, so let's move on the third part. We'll move on to the third part now. Voltage gain. Okay, so voltage gain will be given by AVT. So this voltage gain we will be finding out next. So again, let's go back to the mid frequency small signal equivalent circuit and do some analysis from there. So first of all, we will be calling out certain additions in the circuitry. We'll be adding some voltages of the first stage, second stage, and so on and so forth. So we will be calling this voltage as, let me use a green color to mark that. This voltage we call it as V in. Okay, because V in and Vs are different, they are not the same. Then the output of the first stage, that is over here to ground, we call this voltage as V1. So V1 is the output of the first stage, but the input to the second stage. All right. So with these definitions, let us begin and calculate the voltage gain of the circuit. So let us do that conceptually first, and then we'll write it down simply. So your overall voltage gain will be given by, let me add it over here. Overall voltage gain will be given by V out upon Vs. All right, no doubt about it. We can divide it into V out upon V1. That will be the second stage gain. Then V1 upon V in. That will be the first stage gain. And then V in upon Vs, which is a simple voltage divider. We can easily find out that. All right. Now we have to focus our attention and calculate V out upon V1 first of all. V out upon V1, which will be the gain of the second stage, okay, which we can call it as AV2. And also we need to find V1 upon Vn, that is first stage gain. Okay, so let us do that quickly and then we'll write it systematically. Now, can you tell me what will be V out? From here, what will be V out? So V out will be I out into Re. V out will be I out into Re. And what will be V1? Similarly, what will be V1? Let me take this down. Yeah. What will be V1 voltage? V1 voltage will be this current IB2 into RI2. This current IB2 into RI2. All right. So again, I repeat, what will be V out? V out will be I out into RE, and V1 will be IB2 into RI2, because RI2 is measured from the base terminal to the ground. All right. So let us calculate that now. Let us first write down the gain systematically. So the overall voltage gain AVT will be given by V out upon Vs, which will be V out upon V1, that is V1 upon V in, and that will be V in upon Vs. All right, where this is the second stage gain, this is the first stage gain. All right. So we were finding the second stage gain. So we got the value of V out. V out we got to be I out into RE, and divided by, we write it as V in. V in was IB2 into RI2. Now, if you look carefully, your I out is nothing but IE2, and IE2 divided by IB2 will give you the current gain of the second stage, AI2. Let us look into it. I out upon IB2. Okay. So let us go back to the mid frequency small signal equivalent circuit. Here it is. Fine. So from here we can see that uh, I out upon I out upon IE2, which is 1. IE2 and I out is same. So I out upon IB2 will be AI2, as you can see very, very clearly from here. All right. So from this, we can add it over here that I out upon IB2 is nothing but AI2. So we can write V out upon V1, which is AV2, which is equal to V out upon V1, which will be equal to AI2 into RE divided by RI2. So that will be the voltage gain of the first stage. So voltage gain we can find out with the help of the current gain also, where what is your value of AI2? Where AI2 earlier we found out to be it is 1 plus beta 2. Pretty simple. Okay. And RI2 already we have discussed what is the formula. All right. Now let us find out the next one, that is V1 upon V in. We have found out the value of V out upon V1. Now let's calculate V1 upon V in. Now let's calculate the gain for the first stage. So what will be V1 now? V1 will be again IB2 into RI2. Again, it's the same formula, right? V1, earlier it was IB2 into RI2. This time also same thing. And what will be V in? What will be V in voltage? So V in voltage over here, this voltage will be parallel also to this voltage, right? So what will be V in? V in, we can also write it. I mean, what this is what I'm saying. This also is V in. Okay. So what will be V in now? V in will be equal to this current IB1 into this resistance. What is the resistance from base 1 to the ground? RI1. So here it is. V in will be IB1 into RI1. Are you all following? And what will be V1? V1 will be IB2 into RI2. I hope you all are following this, right? So V in will be this voltages in parallel. So resistance with respect to base 1 with respect to ground will be RI1. All right. And this multiplication of this current IV1 into RI1 will be V in. And V1 will be IB2 into RI2, measured with respect from the base 2 terminal to the ground. All right. So let's write it down formally. So over here we can write V1 upon V in. So what was the V1 value? Is same as IB2 into RI2. And what was the value of V in? It was IB1 into RI1. All right. And let's calculate what is IB1. And IB2 is same as IE1, right? Let us check it out. From here also, IB2 is same as IE1. All right. So IB2 divided by IB1 is nothing but your AI1. IB2 divided by IB1 is nothing but AI1. All right. So let me add it over there. So here we have it as IB2 divided by IB1. IB2 divided by IB1 is nothing but the same as or IE1 divided by IB1 is same as AI1, current gain of the first stage. Okay, so we can rewrite this formula as this expression as AV1, which is the gain of the first stage, will be V1 upon V in, which is nothing but AI1 into RI2 divided by RI1. Okay, so this is the formula for the voltage gain of the first stage. Now only thing left is to calculate the value of V in upon Vs. So let me again go back to the mid frequency equivalent circuit. So this circuit has to be drawn very carefully. It's coming again and again. So over here we have relation between Vs, R sig and V in. Okay, and on this side we have Ri. Okay, don't see this R1 parallel to R2. You have to see this Ri value. So we have Ri in series with R sig, and then we have Vs. So let me redraw the circuit once again for your reference so that we can easily apply the voltage division rule. So we have the following circuit now with us. We have R sig, and then we have Ri over here, and this the voltage over here is Vs plus minus Bs. This is R sig. And where is my V in? This is my V in. Now, by simple voltage division rule, we can find out the value of V in is equal to Ri divided by Ri plus R sig, right, into Vs. So that Vs will bring it down. Okay, so this will be the expression for V in upon Vs. All right. So we got the value of the overall voltage gain. So the overall voltage gain will be, we can write it down over here. AVT will be equal to AV1 into AV2 into Ri upon Ri plus R sig. Okay. So that will be the value of the overall voltage gain. Let me add a blue color over here. Yeah. This is the value of the overall voltage gain of the amplifier. Now, as you can see, one note over here, we can write that R sig, whenever R sig is present, it will reduce the overall voltage gain. So we can write over here, note that R sig reduces voltage gain. And that is always true. If you have a signal resistance, it will always reduce the voltage gain. All right. So we have also find out the output resistance of the circuit. Now, last thing which is remaining is we finding out the, we found out the voltage gain of the circuit. Last thing which is remaining is we have to find out the output resistance. So that is the fourth part. We calculated Rin, we calculated current gain, we now calculated voltage gain. Now, last thing which is left out is output resistance. That is, we can call it as R out. Estimation of R out. Estimation of R out. Okay, fine. So for R out estimation, we might have to draw the circuit again. Now, which circuit are we talking about? We are talking about the mid-frequency equivalent circuit. Okay, why I'm drawing it again? Because already there are too many markings over here. Okay, so let me quickly draw this again. You all can also, you all must have drawn this. So just have a look at it quickly. Okay, so for R out, I required a circuit to be fresh without any markings over there. So let me quickly draw the small signal equivalent circuit for you all. So here we have R sig, then we have R1 parallel to R2 resistance. Then from here to here we have R pi 1 and here we have GM1 into V pi 1. Now this is connected over here, and then here we have, let me draw it like this. Okay, especially I'm drawing it like this for a reason. Here we have R pi 2, and over here we have GM2 into V pi 2. GM2 into V pi 2, right? All right. And finally, I will tell you the reason why I'm doing this way and why I'm drawing this way. It's one and the same circuit only, but I'm drawing it differently. And here we have Vs plus minus. Let me add the plus minus out. So here we have Vs plus minus going towards the ground. This is R sig, and the two collector terminals are tied together and they are connected to the ground. Okay. Now let me mark the terminals. This will be, let me use a red color to mark the terminals. So this will be base 1. This will be emitter 1. And here we have collector 1. This is collector 1. This will be collector 2. And over here we will have emitter. From emitter 2, we will have a resistance R E. And from here to here, we'll have it as a ground. Plus minus V out. All right. So yeah, let's start. Here we can write it as emitter 2. Here this is base 2. Base 2 and emitter 1 are connected together, right? So here I have drawn it slightly modified form. And let me mark the voltage, the value of the voltage at the output of the first stage. So this voltage we call it as plus minus V1. All right. Now this is the same circuit. I'm just extended it out. I'll explain. You will understand automatically why I've done that. Now, for finding the value of R out, what is the first procedure? We have to deactivate the input source. So over here, we'll have to, let me write it down. We have to short circuit. We have to short circuit input source. We have to short circuit input source. All right. So now let's start, and we have to find the output resistance. Now, what do you mean by output resistance? Let me mark with orange color and with a bigger font. Okay. Output resistance is looking into the output terminals. We call it as RO. Let's call it as RO. All right. Now, this RO, if you directly estimate, it will be slightly difficult. So we'll be estimating over here also. This we call it as RO2, output resistance looking into the emitter 2. And then we'll also find out the output resistance looking into the emitter 1 terminal, which we call it as RO1. Now, RO can be found out if you calculate RO2, and RO2 can be found out if you calculate RO1. Okay. So in this simpler manner, we can easily calculate the value of RO. All right. So let's do this technique. Let's find out the value of RO1 first. So now tell me, what will be RO? I mean, this is short circuited, of course. Let me use a, this is connected short circuited. Okay. So this R sig is basically connected to the ground. All right. That means R sig is in parallel to R1, is in parallel to R2. Now these three are they parallel to R pi 1? No, they are in series. So it is R sig parallel to R1, parallel to R2, then plus R pi 1. Okay. Now, what about the current? So over here, the current is IB1. But what is the current over here? IE1. Now, what is the relation between now for this to be plus, we know that the current should be same. So this current also should be emitter current, right? So how will you convert base current into emitter current? How will you convert base current into emitter current? Let me add it over here. Okay, let me bring it down slightly. Okay, so we know that emitter current is emitter IE1 is 1 plus beta 1 times IB1. So we can write IB1 is equal to IE1 divided by 1 plus beta 1. Are you following? Because Rsig parallel to R1 parallel to R2, we can write plus R pi 1, provided this current over here is also IE1. So this IB1 can be IE1 divided by 1 plus beta 1. That means whatever resistance we are writing over here, Rsig parallel to R1 parallel to R2 plus R pi 1, entirety we have to divide it by 1 plus beta 1. Are you following? Because we want the current to be in terms of IE1 now. All right. So let me write it down over here. RO1 will be R6. Let me write equal to properly. Okay. Okay, it's slightly taking some time. Yeah. So RO1 will be equal to R6 parallel to R1 parallel to R2 plus R pi 1, the whole divided by 1 plus beta 1. I hope you're following. Okay. Let me go back and explain again. Right? So we have R6 parallel to R1 parallel to R2. This current is IV1. And this current over here, which is flowing over here, which we are looking into this terminal, that is RO1 will be, this RO1 will be at the emitter terminal. So from the emitter, we have to go to the base. So this emitter current has to be converted into, this base current has to be converted into emitter current, right? Because we are going from output side to the input side now. Okay. If we are going from input to the output, then we write in terms of IB. Now we are going from emitter to base. So everything has to be in terms of emitter. So it will be R6 parallel to R1 parallel to R2 plus R pi 1, the whole divided by IB1. 1 plus beta 1. All right. And next we have to calculate RO1. Exactly in the same manner, we have to calculate RO1. Now tell me what will be RO1. RO2, sorry. So RO2 will be RO1. Now RO1 over here, current will be IB2. Here is IB2. And here the current over here is IE2. So how will you convert IB2? It will be IE2 divided by 1 plus beta 2. Okay. So now it will RO2 will be R pi 2 plus RO1, the whole divided by 1 plus beta 2. Now why we are considering only RO1 over here? Because RO1 is the effective output impedance looking from the emitter 1 terminal towards the ground. Emitter 1 terminal, towards the input side. So we already calculated that. Okay. So this resistance RO1 plus R pi 2. Now, why we are dividing it by 1 plus beta 2? Because again, we are going from emitter to base. We are going from emitter 2 to base 2. So whenever you go to emitter 2 to base 2, you have to convert everything into emitter current. So these two resistances RO1 plus R pi 2 divided by 1 plus beta 2 will be the answer. Now let me write it out. Let me write this out first. So RO2, okay. So we have RO2, which will be RO1 plus R pi 2, the whole divided by 1 plus beta 2. And if you really calculate this with numerical values, this value will be very, very low. We will try to come back to this point when we solve some numerical on this. RO2 will be numerically very, very small. Okay. Now, only thing left is to calculate the value of RO. Now, what will be RO? RO will be RE parallel to RO2. As you can see, they are in parallel. RO2 is measured from emitter 2 with respect to ground. And here we have RE. So we have two resistances in parallel. So RO will be RE parallel to RO2. All right. And normally the value of RE is very small. R out or RO will be equal to RO2 parallel to RE. We know in parallel combination, the value of the resistance will be lower than the lower value. So your RE value is low. So the resistance over here, this is very, very low. So this also will be very low. So this is the output resistance of emitter follower amplifier using Darlington pair. So this is the output resistance of the amplifier. output resistance of the amplifier. All right. And I think with this, we have come to the end of this session. Let me revise quickly what we have done so far. So far we have, started with Darlington pair. Okay. And we have used Darlington pair inside your emitter follower amplifier and, common collector amplifier using Darlington pair. Okay. Using Darlington pair. So for this, we have first done the DC analysis and we calculated the Q point, and then we did AC analysis and we have drawn the mid frequency small signal equivalent circuitry. In AC analysis, we have first find out the input resistance, which came out to be very high. Then we found out the overall current gain AIS. Then we find out the overall voltage gain, that is AVT, and we find out the overall output resistance RO or Rout, right? So that's it for this session. Next time we'll solve a numerical on common collector amplifier or emitter follower using Darlington pair. During that time, all the analysis which we have done in today's lecture will be useful, right? So if you have, be careful to, refer to this analysis before you solve any numerical on Darlington pair, a common emitter amplifier or sorry, common collector amplifier or emitter follower amplifier using Darlington pair. So that will be all for this session. Thank you everyone for patience listening and have a good day.